Okay. Hey guys, it's Mr. Caldwell wanting to go over these kinetic molecular theory and gases notes that you find on Canvas today, Tuesday, April 21st. Hope everybody is well. And let's just jump right into it. I'm not going to insult your intelligence and read to you here, but let's go ahead and jump down here. The kinetic molecular theory and this whole unit that we're kind of digging into here is specifically a deep dive into the behavior of gases. And the kinetic molecular theory, KMT, is a nice part of sort of underpins all the things that we know and excuse me, understand about gases. And it's got a couple of key points here. One, gases relative to the space that gases take up. All right, the particle size of the gas molecules or gas atoms themselves is very, very small. All right, so we have insignificant attractions or repulsions between them. That's an oversimplification, but it works pretty well for most of the situations that we deal with in this introductory level course. Uh, Now, where this starts to break down a little bit is, well, you know what, I'm getting ahead of myself, so I'll just stop there. The second key point here is when we think about particle motion, all right, we're going to assume that the gas particles behave like billiard balls. Like if you go to the pool hall, the ball will it will go in a, a straight line, and the only thing that's going to change the motion of that billiard ball, the only thing that's going to change the motion of that gas molecule is a collision with another gas molecule, right? And in those collisions, no kinetic energy is lost. And we'll get down here to kinetic energy, which we discussed in videos yesterday. Um, no kinetic energy is lost. And the third thing is particles always have energy, and the type of energy that they have is called kinetic energy. And the amount of kinetic energy an object has depends on its mass and its velocity. So if we think about throwing a baseball versus throwing a bowling ball, all right, I can throw a baseball a lot faster, right, because it has less mass, right, than I can throw a bowling ball, all right. So you want to keep that in mind when we talk about a little bit later on in this unit, excuse me, whether I have like a hydrogen molecule or an oxygen molecule. Yesterday, we talked about temperature being a measure of the average kinetic energy of an object. And so if I have hydrogen at 100 degrees and I have oxygen at 100 degrees, they're going to have the same amount of kinetic energy. But what that does mean is because they have the same temperature, that means they have the same kinetic energy. Now, because hydrogen has so small of a mass, right, its velocity is going to be very, very high. That's kind of like throwing a baseball, right? You can throw that baseball really fast because it's light. Now, for the exact same temperature, all right, the oxygen has a much larger mass. And because it has that much larger mass, its velocity has to be slower. It's kind of like you're throwing the bowling ball. All right, so that kind of runs you through the first page there. Second page, all right, couple of properties of gases, some characteristics. Gases are very low density. They take up lots of space relative to solids and liquids. Gases are compressible and expandable, all right? And you can see that as you play with some of these simulations that we're going to be playing with in this unit. Now, two words here, diffusion and effusion. If you have ever walked into a room and you've smelled somebody who maybe has that Axe body spray on, it seems to be something that happens a lot in middle school. All right, you spray some of that Axe body spray on you, all right, and it has some chemicals in it that naturally go into the gaseous state. And because of how gases behave, the particles are just moving really fast in all sorts of different directions. Over time, that Axe body spray smell can diffuse all throughout the room. It just spreads naturally throughout a given space. So, you know, the entire perfume industry is based on diffusion, the idea that gases can naturally fill the space that is provided to them. Effusion is it's related but slightly different. Effusion, think about diffusion, right? So if I were to put a gas in a container and that container had a small opening, right? So these gas particles are all flying around, and eventually, at some point, one of the gas molecules is going to head out, all right? And again, depending on the temperature, because the hotter it is, the faster the particles are moving. If these particles are moving faster, it's likely that they would get out of this opening more quickly. And if you have a lighter substance, that's going to effuse more rapidly out of a closed container with an opening, because that lighter substance is going to be naturally moving faster, just like the bowling ball and the baseball analogy we were talking about. All right. And then one last idea that we need to get at is when we talk about gases, we need to be clear about what the idea of pressure is. All right. It's the amount of force per area. And so I can do pressure is force over area. And there's lots of units for pressure. And we'll worry about the units. Probably we'll discuss those during class time or one of the other videos in the coming days. But I wanted you to understand that there is a couple of different ways that we can measure pressure. And one of them is called a manometer, right? This is an example of a closed tube manometer. So you have basically gas sample, all right, over here. And you have a area over here that is sealed off. And this area that is sealed off has a certain pressure associated with it. And this is containing gas. And here we're saying that it's 105 millimeters, and we'll talk more about that in just a second, or 14 kilopascals. So that's the pressure over here, all right? Or excuse me, that's the pressure actually of the sample. And the reason that we're getting this measurement is because we're looking at the difference in the levels of the liquid. If the pressure in this side of the chamber was exactly the same as the pressure in this side of the chamber, then these liquid heights would be at the same level. You'd have a container that looks like this, and the levels would be equal to each other. Well, I didn't draw that very well. Sorry about that. Now, an open manometer, right? This is going to be open to the atmosphere, right? And so what we can do is we can look at the differences in the levels of the liquid here. And by looking at the differences in the levels of the liquid, you're going to be able to determine how much pressure there is on the inside of this container as compared to the outside. Now here, we've clearly got more pressure on the outside, all right, because this is open to the atmosphere. So the atmosphere is pushing down on the liquid, and it's pushing down on the liquid more than the gas is pushing in here. So you end up with a height difference of this, and you do some thinking and some math, and you can determine the pressure of it. And so what does this all sort of mean? Let me go ahead and zoom this out just a tiny bit. All right. So one of the ways that we can measure, and if you've ever watched a news broadcast, the weather, sometimes they talk about atmospheric pressure is rising or atmospheric pressure is dropping, right? So if you had a tube, it's closed, right? Think about like maybe a test tube. And you took that test tube and you had it submerged in a liquid. You could use water, but water is not nearly as heavy as mercury. Mercury is quite heavy, and that's why we use it in what we would call here a barometer, which measures air pressure. You take it, it's completely submerged, so the tube is completely filled with the liquid, in this case mercury, and you invert it, you turn it upside down. Well, gravity is going to want to pull that liquid down. And as it pulls that liquid down, there's nothing in the tube to replace the liquid that has fallen. So this is now a vacuum, all right? And what you end up with is Out here, you have atmospheric pressure pushing down on the surface of the liquid mercury. Right? So this is just a container that's holding liquid mercury. Atmospheric pressure is pushing down, right? Gravity is trying to pull all of this liquid down out of the container. But because of atmospheric pressure, okay, atmospheric pressure pushes on the liquid out here, gravity pushes here, and eventually this liquid column reaches a level and it's steady. And so normal atmospheric pressure at sea level, the height of this column of mercury is going to be 760 millimeters of mercury. So when we talk about the units for pressure, all right, easiest one is 1 atm, 1 atmosphere of pressure. Well, 1 atmosphere of pressure is 760 millimeters of mercury, right? Now, instead of using millimeters of mercury, sometimes we'll call that 760 torr, named after Alessandro Torricelli, who did some interesting work in the study of gases in Italy. And another unit in a metric system is 101.3 kilopascals, kPa. Now, we're not going to dig too much into these, but just understand that these are 3 common units that we use for pressure. Okay, and that is addressed down here in the table. And one other thing here, the English system, we wouldn't worry if the metric system was being used. We use 101.3 kilopascals. If we're doing it in America, we might be talking about PSI 14.7. If you've ever inflated a bike tire, you probably had to use a bike pump and you inflated it to a certain PSI. That's pounds per square inch. That means that on every square inch of surface in that bike tire, if it's 14.7 psi, you've got 14.7 pounds on that 1 square inch of surface. So here, just a little homework thing. It's not really homework. I just want you to think about it. If I put a balloon outside in the cold or the heat, the balloon will change dramatically. And if we think about, and this is in one of the videos that I think you'll be seeing here soon. If I have a balloon at sort of regular temperature, there's my balloon. The particles are moving around, and as they move around, they slam against the walls of the balloon, and that's what gives the balloon its shape, its volume. Now, if I heat the balloon up, right, if it's hotter, now those particles are moving faster, and as they move faster, they're going to slam against the walls of the balloon with more force, and because they are slamming with more force, it's going to cause the balloon to expand. So there's this really nice relationship between temperature. If the temperature goes up, the volume goes up. This is what we're going to get at with class time and our notes tomorrow. And then conversely, if I cool the balloon and now I make it cold, the particles are now not moving anywhere near as fast. So they're kind of, they're getting cold, they're not moving. And so what you end up with is a smaller balloon, and that's not a ton smaller than the original one. But as the temperature goes down, the volume goes down as well. And there's all sorts of interesting relationships here that exist between different aspects of gases, and we'll explore that tomorrow. All right, sorry that took me so long, but I hope that that's helpful to you guys. Have a wonderful day, and I'll see y'all soon.